so today we're talking about the chemical reactions, and we're talking about the process of balancing, specifically going from skeleton reactions to balanced reactions, going from word to written to word, word to skeleton, skeleton to balanced is the goal. But today we're specifically going from skeleton to balanced. And so in doing so, there's a big overview and then there's a more detailed process. And the big overview is the first thing you're going to have to do is write the skeleton equation. You cannot balance an equation without having properly balanced compounds, which is your skeleton equation. Then you're going to have to remember the conservation of mass, which states matter is neither created nor destroyed, but it can change shape or form, which basically means, as we know in a chemical reactions, things rearrange themselves. So by knowing that things rearrange themselves, but you always have to have the same number of things on both sides. And then you're going to balance the products and reactants so that the reactants equal the products. And when these steps are complete, and remember, this is a really big overview of a detailed process that we're going to be going through, then you will have a balanced reaction. Okay, so after we have the big overview of the process, we can talk about a coefficient. And the coefficient is the number that is written either before the products or before the reactants. It goes in front. Please remember that for our class, we're going to be using whole numbers. There are some exceptions where you might be using fractions, but that isn't covered in a basic general chemistry class. Same rule as the subscripts, a 1 is assumed. So you always write coefficients starting at 2 or higher. The coefficients go in front. They are not subscripts. When you are balancing reactions, we are never going to change a subscript. You balance with coefficients. You balance compounds with subscripts. Balance equations with coefficients, compounds with coefficients. Okay, so let's talk about the 5 or 6 steps to balancing a reaction. Now, when we talk about these steps, these are the big overview steps. We're going to be looking at different ways of approaching these steps because you might do a color-coded method, you might do a counting method, and there's other different ways of doing this, but this is the process. So the first step you always are going to do is write your skeleton equation, because remember, again, you cannot balance a reaction from not balanced compounds. Then you're going to count the number of elements on the reactants and do the same thing for the products, because you need to know the number of each specific atom or polyatomic. Then you're going to change the coefficients to make them equal, because remember, when balancing, you never change a subscript. You're going to always write your coefficients in their lowest possible ratio, and then you're going to go ahead and check your work. So if you're going to be doing color-coded notes, pick out your colors. And the first thing I'm going to do is I'm going to show you 2 different ways to balance. Now, I'm a very visual person, and I totally prefer the color-coded method. So I pretty much balance that way. But if you are a step-by-step person, I'm going to show you one of the multiple different forms of number counting methods. So the first type I'm going to do is I'm going to do a number counting method. Now, I don't care what method you use, because no matter what method you use, you should get the same results. And I'm going to show that to you. So we're going to start with a basic reaction. We're going to do NaOH aqueous plus calcium bromide to aqueous forms calcium hydroxide solid plus sodium bromide aqueous. Now, I almost always put a line down the middle. It really helps me with my counting to determine and to visually separate my products, my reactants from my products. So the first thing we're going to do is I'm going to play this the same way as I would do the color coding one. You can go ahead and choose a color for each of your elements, and you're going to underline them. It'll help you to visually see what's happening. So I'm going to use this nice pinky color for my sodium. I'm going to go ahead and underline sodium color. I do the same over here. The reason I do this is because, especially the color-coded method, but also you don't want a lot of black. I can show you ones where I've done it before. And if you're just doing all in black, it can get very, everything looks the same. So I'm going to do this one, but I'm going to color organize the elements so that you can see. I always underline what colors I'm using for each element, because sometimes I get halfway through a problem and I go, oh no, what color was I using? But if I've already underlined in the color, it'll help me organize myself. So the question you ask yourself is it a standalone element or is it a polyatomic? If it's a standalone element, you know it's going to be found on both sides. It's a standalone element, and you can just underline them. If it's a polyatomic like hydroxide, you always look to the other side to see if the match is there. If you have the same polyatomic on both sides, you can treat it like a standalone element. And I'm going to use this nice kind of purple color for hydroxide. If it is separated, as in there's a hydroxide over here, but there's only an O and an H over here, you have to treat them as separate elements. And that's why you look on both sides. Calcium standalone, so I'm going to go ahead and underline that as a standalone. And then bromine is standalone, and I'm going to go ahead and underline that with this nice kind of orangey color. I'll do that over here. Now that we've organized it, and you don't have to organize it like this for your counting method, but I do want a more organized system so people can really follow my notes. It's up to you. You will have to do the same organization for the color-coded method. You do your count. So for sodium over here, I have 1. And I know I have 1 because there's 1 written and there's no subscripts. And subscripts tell you how many elements are written. So there's 1. So sodium over here, I also have 1. Over here, I have hydroxide, which is OH. And over here, I have 1 hydroxide. Over here, I have 2 hydroxide. That 2 goes to that hydroxide. Remember, if it's in parentheses, a subscript goes exactly with what it attaches to. It does not distribute. So that 2 goes to that hydroxide, and I have 2 of them. Then I look at my calcium here. I have 1 calcium. And I have 1 calcium over here. Over here, I have 2 bromines. That 2 is a subscript that goes with bromine. And over here, I have 1 bromine. Okay, now that I've done this count, I can compare. I have 1 sodium, 1 sodium. Okay, we're balanced. I have 1 hydroxide. I have 2 hydroxide. I'm not balanced. I need to fix that, but I can continue looking. I have 1 calcium, 2 bromine, 1 bromine. My bromine isn't balanced either. Now, the trick that I always say is if you have an element like this that are 2 single elements that are standalone, that are only going to be balanced, that there's just 1 of each of them, use that last, because then you can just balance with a coefficient, and there's no additional subscripts that are going to be balanced. So I'm going to, because of that, and because I always try to balance my compounds first, I'm going to start balancing with my sodium hydroxide. I have 1 hydroxide over here. I have 2 hydroxide over here, and you're only going to change 1 coefficient at a time. So I ask myself, what times 1 will equal 2? Well, the answer is 2. So I turn that 2 into a coefficient. So I put a 2 in front, and then I write NaOH. Now, coefficients, unlike subscripts, do distribute. So this means I will have 2 sodiums and then 2 hydroxides. Now I've changed a coefficient here, which means everything else should remain the same. So I just copy it down exactly. Okay, because we changed a coefficient, we now have to redo our count. So now I have sodium over here. So it distributes, so I have 1 sodium. Sorry, I have 1 sodium here, but because I put the 2, 2 times 1 is 2, so I now have 2 sodiums. Over here, I still have 1 sodium. My hydroxide is OH. 2 times OH is 2, so I have 2 hydroxides. And over here, I still have 2 hydroxides. My calcium, I still have 1. I didn't change anything, so I have 1 calcium here. And I have 1 calcium here. There's no coefficient. For bromine, I have a subscript of 2 here, so I still have 2 bromines. Sorry, I grabbed the wrong color. Sorry, guys. That's supposed to be yellow. And over here, I still have 1 bromine. Well, now we can look at this again. My sodiums aren't balanced. I have 2, I have 1 over here. My bromines aren't balanced. I have 2 over here, I have 1 over here. My hydroxides are balanced, my calciums are balanced. So I really need to look at this one now. So that means I can write this equation down and then add a coefficient to this one. So we're rewriting the equation. So we have 2 NaOH aqueous plus Ca Br2 aqueous forms CaOH2 solid plus, well, now I need 2 sodiums and 2 bromines. I have 1 right now, so I have to add a coefficient out front of 2 in order to distribute the 2 and get 2 of each of them. Okay, now I do a final count, is I think I'm balanced. There's only that one thing that was off, but then I can do my final count, and then I can ensure that I'm balanced and I can write my balanced equation. So again, we're going to color code and do our final count. I have 2 sodium still. And the reason we do this is sometimes when you change a coefficient, you end up accidentally unbalancing it. And so if you change one coefficient at a time, you're going back and forth and keep doing a count, then you can make sure that if you unbalance it by doing a count, you know what you added and you know what you have to correct. And sometimes it's by addressing another coefficient. And sometimes it's by undoing what you did and reevaluating. We have 2 sodium over here now. Now we have hydroxide. Where did my purple go? Sorry, guys. So over here, we still have 2 hydroxide because 2 times 1 is 2. And over here, we still have 2 hydroxides. Now, if we're looking at calcium, over here, we have 1 calcium because if that 2 doesn't distribute to calcium, just to bromine. And same here, we only have 1, sorry, that was 1 calcium. I said 2 and meant 1, and over here we still have 1 calcium. And finally, I have 2 bromines, the 2 here and the 2 there. We can compare sodium 2, hydroxide 2, calcium 1, bromine 2. We are balanced. So we can go ahead and write our coefficients in front of our balanced reaction. We can put a 2 right here and a 2 right here. And that is a balanced reaction. And that is our number counting method. Okay, let's talk about the next method now, which is going to be a color coding method. So I'm going to put a line here so you can see the difference. And then I'm legitimately going to do the exact same equation with a color coding method or the color molecule method, however you want to call it. Now, I personally believe this method is easier to see what's happening, but I'm a very visual person. So this works for me. If you're a numbers person, this will work for you. And then there's another number method where you can just line them up back to back and count that way. There's a lot of different ways of balancing equations. Please find the way that works for you. You will always get the right number. So let me show you the color coding or the colored molecule method. Stay. So we have NaOH, AQ plus CaBr2, and that forms CaOH2 solid plus NaBrAQ. Now, same thing. I'm going to put a line down the middle. Probably doesn't have to be as big of a line, but same line. And you're going to follow the same steps as you did before with underlining in color. But it's really important this time that you make sure that you're using the same colors. So, and following the steps. So sodium is my first element. It's an element. That means I don't have to think about if it's on the other side. I just underline it and do the same for this sodium over here. Really important to follow your colors now. The next element we're doing is hydroxide. Hydroxide's a polyatomic. We have an OH over here. We have an OH here. Hydroxide is found in full on both sides, so I can treat it like a single element. So I'm going to underline this hydroxide in yellow over here and this hydroxide in yellow over here. Calcium is an element, so I can just treat it like one. So I get to underline a calcium here and a calcium here. And finally, we have bromine, which is again a single element. So I'm going to underline this bromine here and this bromine over here. Now, on this method, what you're doing is you're going to be visualizing the molecules. And it's important to understand that, yes, you underline, but don't just start putting dots. You have to develop a molecule and you have to make sure what you're developing touches, because you can't just randomly add a piece. You have to make sure you're representing the whole molecule every time. So if I'm going to represent one sodium by writing a dot, then I have to represent always one hydroxide, because for every time you add a sodium, you add one hydroxide. And those are always together. We can do this for calcium too. For every one calcium here I add 2 bromides. And it's always. You always have to represent the whole molecule. You can't just add part of a molecule. You've got to represent the whole molecule. For calcium hydroxide, for every 1 calcium we add, 2 of your hydroxide atoms are being added. And they're being added every time, so you can have them touching the calcium atom. For sodium bromide, for every 1 sodium you're adding 1 bromide. They come as a pair. You can't just add a sodium without adding a bromide. And you always draw at least 1 of everything, because you know at a minimum you're going to have 1 of everything. Now what you do is I look at the colors. I have 1 pink, I have 1 pink, we're balanced. I have 1 orange, I have 2 oranges over here, we're not balanced. I have 1 dark pink, I have 1 dark pink, maybe it's mauve, we're balanced. I have 2 blues, 1 blue, the blues aren't balanced. So I can start by adding a blue. So I'm going to add a blue over here. And remember, every blue, which is bromide, comes with a side of sodium. So I can add that over here. You can't just add a blue bromide without adding your sodium. They come as a pair. You have to make sure that every time you add 1 piece of a molecule, you add the rest of the molecule. Now I have 2 blues. My blues are happy. But now I have 2 pinks over here and 2 yellows, and I only have 1 of each. So I can add 1 more molecule. So I'm going to add 1 more sodium to match here. Every sodium comes with a side of hydroxide. You have to represent the whole molecule. So I'm going to draw the whole molecule. Now I have 2 hydroxides, 2 hydroxides, 2 pinks, 2 pinks, 1 mauve, 2 blues, 2 blues. I'm balanced. Now I can go back and write my coefficients. And what I've done is visualize my coefficients. So I have 2 down here. So my coefficient is 2 because that tells you how many you need. I need 2 of the molecule, so I write 2 out front. I need 1 calcium bromide, so I don't have to write it as a coefficient because coefficients only start at 2. I have 1 calcium hydroxide, and again, I don't have to write it as a coefficient because coefficients only start at 2. I have 2 sodium bromides, so I write a 2 in front of my sodium bromide because I need 2 of them. And that's the basis of the color coding method. Okay, let's do another example. We're going to do NaNO3 plus PbO forms PbNO3 2 plus Na2O. And we're going to just draw a line right down the middle. Just keep it organized so you make sure that you're visualizing your reactants and your products. And remember, your first step is to always underline so that you know what you're using for your reactants and your products. So sodium's my first. Sodium is an element, so I know it's going to be on both sides as sodium. So I'm going to go ahead and underline it. Go ahead and underline it. Sorry, I just took a pause to make sure I was actually recording. And then I'm going to go ahead and look at nitrate. Nitrate's a polyatomic, which means it can either be broken up into sodium and oxygen sometimes when it gets switched, or it could stay as a polyatomic as NO3. NO3 is on both sides exactly the same, so I can treat it as one element. If it was not exactly the same, such as it was NO or NO2 or NO4, I'd have to break them apart into different elements. It has to be exactly the same on both sides to be counted as a single element. Now I'm going to look at PB and O. Their PB and O are all single elements, can be found on the periodic table, so I can treat them as such. So underline PB is going to be blue. And O is going to be this kind of magenta mauve color that I've been using. Now, once I color code everything, the very next step is to always ensure that I've drawn at least one of each. And remember, you're representing the molecules, so you have to draw it as it's written. I have 1 sodium, 1 nitrate, so I have 1 sodium, 1 nitrate. I have 1 PB and 1 O, so I draw 1 PB and 1 O. And remember, you're drawing a molecule, so you have to make another one. We need 1 more PB to make sure you're adding a whole PB and a whole nother O. Over here, I have 1 PB and 2 nitrates. And I know I have 2 nitrates because I have this subscript over here. That subscript goes to nitrate, especially seeing it's in parentheses. It does not distribute over to PB. Make sure that you remember that. Subscripts don't distribute, coefficients do. And I have 2 nitrates, so I'm going to represent them like that. Over here, I have 2 sodiums. And for every 2 sodiums, I have 1 oxygen. Now I can kind of look and see what's unbalanced. I have 2 sodiums over here. I have 1 sodium over here. I have 2 nitrates over here. I only have 1 nitrate over here. I have 1 lead and 1 lead that's balanced. I have 1 oxygen and 1 oxygen that is balanced. So really, to make it balanced, I have to add another one of these because I need both another sodium and another nitrate. So I'm going to go ahead and build myself another sodium nitrate. Remember, you can't just add one, you have to add both. Sometimes you do have to go back and forth. It isn't always just a 1 element add. Sometimes you have to go back and forth and tweak it, and that is okay. But for now, I can look, I have 2 sodium, my sodiums are balanced. I have 2 nitrate, I have 2 nitrates, my nitrates are balanced. I have 1 lead, I have 1 lead, my leads are balanced. I have 1 oxygen and 1 oxygen, my oxygens are balanced. So now I can go ahead and write my coefficients. Remember, when you're doing the color-coded or the color molecule techniques, your coefficients are the amount of molecules you have. So I have 1, 2 of the sodium nitrate, so that 2 becomes my coefficient. Over here, I have 1 of my lead 2 oxide, that 1 becomes my coefficient, but because I've already written lead 2 oxide once, I don't have to write it again. For my lead 2 nitrate, I only have 1, and because I've already written it once, as in writing lead 2 nitrate down, I don't have to write a coefficient of 1. Remember, coefficients are always 2 or higher, and for sodium oxide, I only have 1. And again, I wrote it the first time, that was writing the balanced compound, so I don't have to write 1 as a coefficient. Okay, let's do one final example. So we're going to do Ag, Br plus Ga, PO4, which will form Ag3, PO4 plus Ga, Br3. And yes, normally they should have states of matter on these. These don't, because the worksheet I pulled them from didn't give them to me, and I didn't have the time to look them up. But normally you would be given states of matter. So remember, your first step is to always outline your color coding. So for this one, for silver, silver is an element on the periodic table, so I know I'm going to find it on both sides. I'm just going to go ahead and use this pinky color. For bromine, again, bromine is an element on the periodic table, so I'm just going to go ahead and outline that as a blue color. Gallium is again an element on the periodic table, so I'm going to go ahead and use that, this lovely kind of mauve color on it. And phosphate, I can see it clearly on both sides, so it's a polyatomic, but it's found on both sides, so I can use it as 1. Remember, polyatomics that are not the same on both sides do have to be considered into their separate elements. So you've got to double check your polyatomics. So for silver bromine, I'm just going to go ahead and build my elements now, because that's the next step. So for every 1 silver, I have 1 bromine. For gallium phosphate, for every 1 gallium, I have 1 phosphate. So you've got to remember that you're building these molecules in a visual format, and you have to make sure that you're representing correctly the amounts of each thing. So over here for silver 1 phosphate, I have 3 silvers. That's the wrong color, I apologize. I have 3 silvers, 1, 2, 3, and for every 3 silvers, I have 1 phosphate. And again, I'm having fun with colors, I'm sorry, I have 1 phosphate. And over here, I have this gallium, which is for every 1 gallium, I have 3 bromines. So now that you've represented it, you can compare. I have 1 gallium here, I have 1 gallium here. I have 1 phosphate here, I have 1 phosphate here. I know it's kind of dark. I'm going to see if I can change the color for you so that you can see it better. That's phosphate. Sorry, guys. I have 1 silver. I have 3 silvers. I have 1 bromine. I have 3 bromines. I have 1. I have to add 2 more of these to balance them out so that they're 3. So remember, for every 1 you add, you have to make sure you're adding a molecule. So I'm going to, if I have 1 bromine here, I need 3. So I need to add 2 more bromines. But remember, for every 1 bromine you add, you have to add a silver. So, because you've got to make the whole molecule. So now I have 3 silvers, I'm balanced, 3 bromines, I'm balanced. And then you can write your coefficients. The coefficient here is 1, 2, 3 because I have 3 molecules of it. I have 1 molecule of gallium, so I don't have to write a coefficient because I already wrote it 1 time. I only have 1 molecule and 1 molecule, so no coefficients because coefficients are 3 and higher.